Hello students, welcome to the online lecture series of digital communication. Today we are going to start the fifth unit, that is passband digital transmission. Myself, Assistant Professor Mr. V.R. Vadekar from Matoshi College of Engineering and Research Center, Nasik. Here is the content of your unit 5th. In this, we are going to study the passband transmission model, then signal space diagram, generation and detection, error probability, power spectra of your BPSK, BFSK, QPSK. We are going to study the non-coherent of it, then M-ary PSK, CAM. These are the content that we are going to study in this unit. The reference for this unit we are going to use is of Simon Haken, that is digital communication system, and second is your by Dr. Sanjay Sharma, it is of communication system. Now, in our previous lecture, as we have studied or we discussed that the baseband pulse transmission, in that baseband pulse transmission, the input data is represented in the form of what? Pulse amplitude modulation, that is line codes. So these signals are transmitted over a low pass channel, and this baseband signals, it has adequately large power at low frequencies, but since they have a large power at low frequencies, so that can be easily transmitted over your wires or coaxial cables. But we couldn't transmit it over the radio links or satellite because the impractical size length of your height of your antenna. So that's why it is needed to shift the spectrum of this baseband signal to this high frequency spectrum. So which could be achieved by using the baseband signal to modulate what? This carrier signal. And this baseband digital signal which is going to modulate your carrier signal, this process, it is called what? Digital modulation technique, or it is also called as passband transmission channels or communication, or we can also call it as what? Band pass communication transmission. Now these signals are transmitted over a band pass channel, and the example of this band pass channel, it is what? It could be your microwave radio links, or it could be your satellite channels. So that's why it is necessary to introduce this unit in your syllabus. So we expect, so what are the objectives of this unit? So we expect from the student that they should be able to understand what is passband transmission model, then what is coherent and non-coherent digital modulation techniques, understand generation and detection of your BPSK, then their geometrical representation of it, and then understand what is M-ary, PSK, CAM. Along with BPSK, we also going to study BFSK and QPSK. Now, after completion of this unit, the students will able to understand the difference between your coherent and non-coherent digital modulation techniques. Then they would understand the power spectra of BPSK, BFSK, QPSK, then the error probability of it. They can also understand the generation and detection of them. Then we are also going to, they are going to understand how the generation and the detection of your M-ary, PSK and CAM, it is going to happen. Today, we are going to see digital modulation techniques. What is the difference between coherent and non-coherent digital modulation techniques? Then we are going to see the passband transmission model, then generation and detection of your BPSK, and afterwards we are going to see the error probability and the power spectra of BPSK. So starting with our today's topic, the three basic signaling schemes that we are going to use are your amplitude shift keying, phase shift keying, and frequency shift keying. These are the special class of your amplitude modulation, phase modulation, and frequency modulation. Now, in the transmission and reception of your digital carrier signal, we use modulation at transmitter and demodulation at your receiver. So usually both these devices are packed in a one unit that is called modem, which is used for what? Two-way duplex communication. As you can see on this screen, that amplitude shift keying is basically amplitude is going to shift. So you can see on the screen that for 0, no amplitude it is there, whereas for binary 1, here is some amplitude it is there. Similarly for phase shift keying, since it is a phase shift, so depending on the transition from 0 to 1 or 1 to 0 transition, there is a changes at the phase of the signal. So you can see from 0 to 1 transition it is there, then it is a phase shift it is there. So phase shift, it could be your 180 degree, it could be your 90 degree, it could be 45, depending on the selection. After that it comes a FSK, that is a frequency shift. So in this, we are going to select a particular frequency for binary 0, and for 1 we are going to select another frequency. So usually we select a high frequency for binary 1 and low frequency for your binary 0. Next, we are going to see the hierarchy of digital modulation techniques. So depending on whether the receiver does phase recovery or not, the modulation techniques are divided into coherent modulation technique and non-coherent modulation technique. After that, the modulation technique, it could be your binary or it could be your M-ary schemes. Since the name is binary, as its name suggests, binary means 2. So it is going to use a 2 symbol levels, that is 0 and 1. After that, M-ary schemes, if more than 2 symbols are there, then how we are going to use? So for that, a special class it is there, that is M-ary ASK, M-ary or PSK, and M-ary or FSK it is there. Also, there is a hybrid M-ary schemes, that is your quadrature amplitude modulation, that is called as CAM. It is basically preferred in order to preserve the bandwidth. Usually it takes less bandwidth, but at the expense of your increased power. So what is coherent and non-coherent digital modulation technique? Now the transmitter and the receiver are required to be what? Synchronized in both carrier phase and bit timing. Whereas in non-coherent technique, the transmitter and receiver are not required to be synchronized in both carrier phase and bit timing. Also, coherent techniques are complex because transmitter and receiver, they need to be synchronized, but they are going to give you the or provides you the guarantee of better performance. Next, it is your non-coherent techniques. Non-coherent techniques are less complex, but the performance is not good as that of your coherent techniques. Now, this is the category of your M-ary digital communication. So you can see over here, here are 4. Why 4? Because 2 symbols are there. One symbol is 0, 0, then 0, 1, second, third symbol it is a 1, 0, and fourth symbol it is 1, 1. So in 4-array amplitude shift keying, we have selected the 4 amplitudes. For 0, 0, we have selected no amplitude, whereas for Double one, we have selected the maximum amplitude. For 1 0, it is a moderate amplitude, and for 0 1, it is what? Minimum amplitude. And the duration of each bit is denoted by TB, and the symbol duration, it is denoted by capital T. Next, it is your 4-array phase shift keying. So again, depending on the transition from 0 0 to 1 1, or it could be 0 0 to 0 1 or 0 1 to 1 0, we are going to select the phase. So as I already told, the phase selection, it could be your 180-degree, 45-degree, 90-degree, depending on the transition. Next is your frequency shift keying. In that also, we have taken the 4 frequencies because 4 symbols are there. So suppose for 0 0 minimum frequency it is there, then for 1 1 maximum frequency it is there, again for then 0 1 different frequency, and for 1 0 different frequency it is there. Next categories of M-ary digital communication, it is your constant envelope versus non-constant envelope. So in this also you can see that since it is a constant envelope in the sense what? This envelope amplitude, it remains same, and amplitude, it remains same in BPSK as well as FSK only. So that's why this is called what? Constant envelope technique. Whereas non-constant envelope technique, in the sense you can see on the screen, the envelope, the amplitude is going to change. So you can see on the screen that for 0 0 no amplitude it is there, for 1 1 maximum amplitude, for 0 1 minimum it is there, and for 1 0 moderate, that is in between your 0 1 and 1 1 amplitude it is there. So it is called what? Non-constant envelope. Now starting with your passband transmission model. So you can see on the screen that this is your message source which is going to produce your message. This is a transmitter, signal transmission encoder, and modulator, it is going to form your transmitter. Output of modulator, it has been given to your communication channel. And then this is your receiver section, which consists of your detector and signal transmission decoder. And this is nothing but your output, which is the estimate of the message M, because we are going to estimate. Why? Because noise, it is also one of the parameter it is there which is going to be added at this communication channel. So let's see each block one by one. Now first is your transmitter side, that is message source. It is going to emit or produce a symbol every t seconds. A symbol belongs to an alphabet of M symbols, that is denoted by our M1, M2, M3 up to MM. Now the probabilities of these symbols, say it is a P of M1, P of M2, P of M3, and so on. So this is going to specify what? Message source output. So if all the probabilities are of equiprobable, it means when the symbols are equally likely to get occur, then we can show it that P of I is equal to P of M-ary, which is given by 1 upon M, because 1 upon M for every symbol, because it is what? Equiprobable, equally likely. Next, the output of message source, it has been given to this encoder, which is going to produce a vector, say Si, which is made up of n elements. Then the output of encoder, it has been given to modulator. Modulator, it is going to construct a distinct signal that is of Si of t. T because it is of what? Duration t seconds. So the output Si, basically it is what? Energy signal. That is means real valued signals. And the modulation that could be used over here, it could be your ASK, FSK and PSK. Now this value of this energy signal, it could be given as E of I, which is equal to integration from 0 to t, because it is of duration t second. So energy of the signal, it is given by SI square of t dt, where I equal to 1 to m. M, it is not what? Number of symbols. Now talking about a channel. Since it is a linear channel wide enough to accommodate the transmission of the modulated signal with negligible and no distortion, because this is a characteristic that we expect from the channel. Also, the channel white noise, it is a sample function of your white Gaussian noise. As we know, in previous lecture we have studied the white Gaussian noise, it has what? Zero mean and power spectral density of N0 by T over the large frequency range. Talking about a receiver side. So receiver side, basically it consists of your detector and signal transmission decoder. So what are the functions of this receiver? It reverses the operation performed in the transmitter. Also, it should minimize the effect of this channel noise which is present at this channel, and it is going to give you what? Estimation of this transmitted symbol M. Now starting with our actual topic, that is BPSK, binary phase shift keying. Remember, we are going to see what? Coherent BPSK, and as you know that what is coherent. Since it is a binary phase shift keying, it means binary symbol 1 and 0, they are going to modulate what? Phase of the carrier. So let the carrier, it is given by S of t is equal to A cos 2 pi FCT. So over here, A, it is going to represent what? The peak value of the sinusoidal carrier, and suppose we are going to consider the 1 ohm load resistor, then what would be the power dissipated? It is given by what? Half of A square, that is A is nothing but your amplitude. So we can write it A is equal to under root of 2p, make it as equation number 2. When the symbol is changed, the phase of the carrier is changed by pi radian. So consider, for example, for symbol 1, S1 of t is equal to what? It would be under root of 2p cos 2 pi FCT. FC, it is your carrier frequency. So it is for symbol 1. But if it is symbol 0, then what is S of 2t? It would be what? Cos 2 pi FCT plus pi, it is there because phase change it has occurred when 0 it is there, and pi in the sense it is what? 180 degree. Since as we know that cos pi plus theta is equal to what? Minus cos theta. So we can write this above equation as what? S of 2t is equal to minus this under root of 2p. So we can write it as minus under root of 2p cos 2 pi FCT, because cos theta plus pi is equal to minus cos theta. So it is minus square root of 2p. So make it as equation number 5th. So with above equation, we can define BPSK signal. It would be what? S of t, combination of S1 of t and S2 of t. We can write it as a what? B of t square root of 2p cos 2 pi FCT. Here, what is B of t? It is your plus 1 when binary 1 is transmitted, and minus 1 when binary 0 is transmitted. This is a graph of your binary sequence, and this is a graph of your NRZ signal. So basically at the transmitter side, this binary sequence is converted into your NRZ signal, since it is what? Non-return to 0. So you can see it for bit 1, since it is a NRZ and it is a bipolar. So 1 it is represented by +1 amplitude and 0 is represented by -1 amplitude. And since it is a non-return to 0, it is going to take the entire bit duration. It is not coming it between this mid of this any bits or center of this bit. Now this is the block diagram of your transmitter. In previous figure, I shown you that how the binary data is converted into your bipolar NRZ signal. And this output of this bipolar NRZ encoder, it has been given to what? Balance modulator, which has the input carrier signal. Because this bipolar NRZ, it is going to modulate the phase of this carrier, and the output it would be what? Your BPSK signal. So the BPSK signal, it can be generated by applying a carrier signal to this balance modulator. And this NRZ level encoder, what it converts the binary data sequence into bipolar NRZ signal that we already seen. And this baseband signal B of t is applied as what? A modulating signal to the balance modulator. So whose equation is BPSK? The equation it is given of what? B of t square root of 2p cos 2 pi fc t. Now we are going to see the reception at the receiver, how the receiver it looks. So when this BPSK signal it is transmitted, it is received by this what? Receiver. So you can see from the figure that BPSK signal, there are different blocks are there. First is your square law device, it is there, band pass filter it is there, and frequency divider circuit is there. So basically these three sections together, it is used for what? Recovery of your carrier signal. And this is your synchronized demodulator it is there, which needs to what? Demodulate this BPSK signal. So it has a two inputs, one your BPSK signal and another it is your regenerated carrier signal, that is your reference signal. After that, output of this synchronous demodulator it is given to your integrator and this your bit synchronizer. And this is your decision device. This is your final output. Now we are going to see the each block one by one. First, as you know that the signal, if it undergoes the phase change depending on the time delay from the transmitter to receiver, so this phase change is normally fixed phase shift. We have assumed that phase it should be, it is like say it is a theta it is there, and therefore the signal at the input of receiver it could be written as what? B of t 2p cos 2 pi fct plus theta, because we have assumed that there is a phase shift it has been taken place at this your receiver side. Now first block that we have seen, it is a square law device. The carrier from the square law device is separated, since this is what? Coherent detection it is there. As shown in above figure, we have seen in that receiver section that received signal it is passed through what? Square law device. Why we are going to put it to the square law device? In order to generate the carrier signal. So at the output of square law device, the signal it would be what? Cos square 2 pi fct plus theta. Now we have ignored the amplitude section over here because we are need to interested only for this carrier signal. So in order to simplify this equation, we have ignored this amplitude factor. After that one, as we know that cos square theta it is given by what? 1 plus 2 cos theta by 2. So we can write it cos square 2 pi fct plus theta is equal to 1 plus 2 cos 2 pi f naught t plus theta by 2. So over here f naught and fc it is one and same. Fc or f naught it is what? Your carrier frequency it is there. So therefore we can separate this term. So we can write this 1/2 plus 1/2 cos 2 pi f naught t plus theta. Here 1/2 it is not, it is going to represent what? DC level. So this equation 8, as it would become what? Cos square 2 pi fct theta is equal to what? 1/2 plus 1/2 cos 2 pi fct plus theta. F naught fc is one and same. Make it as equation number 9. This 1/2, it is your DC component, and this is your second harmonic of your carrier. So this is the output of your square law device. Now, the output of square law device, it is given to band pass filter. Since this band pass filter, whose pass band it is centered about around what? 2fc, band pass filter, it is going to remove your DC level, that is 1/2. And so what would be the output? So output, it is what? Cos 2 pi fct plus theta. And this signal has a frequency of what? 2fc. Next, the output is given to the what? Frequency divider input. The bandpass filter output is given to the frequency divider. Why frequency divider? In order to divide this this one by 2. So that's why the output of frequency divider, we get a carrier signal frequency whose frequency is fc, because the band pass filter, it has a carrier frequency around 2fc. So frequency divider, it is going to divide by 2. So we are going to get the frequency at fc only. So this is your required equation, that is cos 2 pi fct plus theta. I hope along with me you also write the equation so that you can easily understood it. After that one, this output of frequency divider, it is given to synchronous demodulator. Synchronous demodulator, or it multiplies what? Input signal and the recovered carrier. So therefore, the output of multiplier, it would be what? We can write it as this one. As you know that cos square theta is equal to 1 plus cos theta by half. So it would become b of t square root of 2p 1/2 1 plus cos 2 pi fct plus theta. Since it is what? It is your received signal. So how we can rearrange this equation and we can write the output of this multiplier circuit, it is there. So this is your final equation. We can write it in this term also, that you can take this 2 inside the square root. So it would become b of t square root of p by 2 1 plus cos 2 pi fct plus theta. Make it as equation number 10. Now the output of this synchronous demodulator, it is given to what? Bit synchronizer and integrator. So above signal is then applied to this, and the integrator, it is going to integrate the signal over 1 bit period. And the bit synchronizer, it takes care of what it does. It is going to decide the start and the end of the bit. So at the end of a bit duration, that is TB, the bit synchronizer, it closes the switch S2 temporarily, and this connects the output of integrator to the decision device, which is equivalent to the sampling of the output of your integrator. And the output of this synchronizer, it is given by this equation. So make it as equation number 11. Now you can see on the screen that how BPSK signal it is going to look. This is your binary data 10111. This is your binary waveform, and this is your carrier. And how your BPSK signal it would look. What is the waveform of this? So you can see that every transition from 1 to 0 or 0 to 1, there is a phase shift, it is there. But if the symbol 1 1 it is there, no phase transition it is there. Again transition from 1 to 0, so phase transition it taken place at this instant and at this instant also. Now we would see the geometrical representation of your BPSK. From equation 6, as you know, that we have written that B of S of t is equal to what? B of t square root of 2p cos 2 pi fct. So let rearrange this equation. So by rearranging, we can write it as square root of p tb into square root of 2 by tb. So by this form, this term, let denote this as phi 1 of t, which is nothing but your square root of 2 by tb. Tb, it is nothing your bit duration. It is cos 2 pi fct. Fc is nothing your carrier frequency. So let make it as equation number 3 and substitute this phi 1, this value in equation 13. So the next equation you would get it what? S of t is equal to b of t square root of p tb phi 1 of t. Make it as equation number 14. The bit energy EB is defined in terms of the power and the bit duration TB as EB is equal to P TB. So make it as equation number 15. We can write then S of t is equal to plus minus what? EB. Phi 1 of t. What is EB? EB, it is nothing but your power into this TB. That is the power content of the signal in the bit duration. Make it as equation number 16. So S of t, it could be your plus minus under root of EB phi 1 of t. So the transmitted signals, it could be represented as S1 of t, that is square root of EB phi 1 of t, equation number 17. And next equation number 18, it would be minus of EB phi 1 of t. So the transmitted signals, it could be the positive or it could be negative. So for transmission binary 1, it is positive, and for transmission of binary 0, it is represented as minus sign. So a coherent BPSK system, it can be categorized by having a signal space that is one dimensional. So with signal constellation consisting of two message points, since over here it is a binary, so m equal to what? 2 it is there. So the coordinates of the message points are what? We can take it as S1 of t integration S1 of t or phi 1 of t, that is nothing but what? Plus of EB. And this is minus AB. So this is your geometrical representation of your BPSK. This is phi 1 of t, and this is the message points 1 and 2, which is denotes what? Plus under root of EB, and this is minus under root of EB. The distance between these two message points is called Euclidean distance, denoted by small d, and this is your 0. So the distance, it is equal to square root of EB plus square root of EB minus of this message point 2, that is minus of EB. It would become what? Twice of EB. So this distance d, it is going to increase the isolation between this symbols in BPSK signal, and hence the probability of error, it is going to reduce as the distance is going to increase. Or you can see from on this graph, this is your decision boundary, it is there, which is 0, and this region, it is called region Z1. As I shown you, this is message point 1, this is message point 2. So how you can represent the geometrical representation of your BPSK signal? Now next, moving towards the error probability of your binary PSK. So based on the maximum likelihood decision algorithm, which is in this case means that we have to choose the message point closest to the received signal point. So for BPSK, as we know n equal to 1, the space is divided into two areas, that is Z1 and Z2. So the Z points closest to the message point 1 at plus square root of EB, and the set of points closest to the message point 2 at minus EB. So it simply decide that S1 of t, it is nothing but your binary 1, was transmitted if the received signal it falls in the region Z1, and it decides that signal S2 of t, that is binary 0, is transmitted if the received signal it is falls in the region Z of 2. There are two kinds of errors are possible due to the noise. That is, if S1 of t it has been sent but it falls in Z2 region, then how we can recognize that bit whether it is a 0 or 1. And similarly, if it S2 of t, that is a 0, it has been transmitted but it is going to fall in the region of Z1, that is of in binary 1, then how we are going to decide binary 0 it has been received or 1 or transmitted? Considering error of second kind, it could be, the signal space is symmetric about the origin. So the probability of both the point, it is same. So the average probability of the symbol error, it is given by this 1/2 error function of this square root of EB by N0. In your syllabus, there is no need to derive this expression. You can directly write this equation of your probability error. So it is going to tell you that increasing the signal energy per bit, it makes the point plus square root of EB and minus square root of EB move farther apart, which corresponds to what? Reducing the error probability. As these two message points, it would move apart from each other, the Euclidean distance it is going to increase, the error probability it is going to reduce. Next, moving towards the power spectrum of your binary phase shift keying. Now from the modulator, the complex envelope of BPSK, it has only what? In phase component. So depending on whether we have a symbol 1 or 0 during this interval, that is 0 to TB, this in phase component we can written as a plus G of t or minus G of t. So from this equation you can write this one. This G of t, it is nothing but your shaping function. So we assume that input binary, it is a random. So symbol 1 and 0 equiprobable or equally likely. Then these symbols transmitted during the different time slot are what? Statistically independent. So the power spectra of such random signal wave, it could be given as, it is GB of f is equal to PSTB sine of pi of TB upon pi of TB whole square. And this above equation is nothing but your power spectral density of your baseband signal B of t, which is also denoted by S of f. So in few book, it could be denoted as S of f or GB of f, which is one and same, which is nothing but power spectral density of your signal. After that, this is the power spectral density of your BPSK signal. Again, in this also you need not to derive this equation, which is obtained, this BPSK is how it is obtained by modulating a carrier with baseband signal B of t. So due to modulation of your carrier frequency, the spectral components are translated from F to Fc plus F and Fc minus F. So you can see that from the power spectrum of your B of t, how the power it is going to shift, the spectrum components it has been shifted. That is for F minus 0, see Fc or F naught, it is one and same. So the magnitude of this component, it is divided by this half, and it is what? PSD of your BPSK signal, which is also denoted by your SBPSK. It is a GBPSK. It could be also denoted by S of FBPSK. So it is one and same. So this is your power spectra of your BPSK signal. This is the power spectra of your NRZ data. You can see whose amplitude is given by PSTB, and mostly the power it is present in this main lobe, which is from FB to minus FB. So this bandwidth is what? FB minus of FB, that is 2 FB. So this is the equation. It is a sinc function. So that's why the graph, it is, it is a sinc wave it is there. As we know, sine of theta by theta is what? Sinc of theta. And this is the power spectra of your what? Binary PSK, which has been given by this equation. So you can see that the amplitude, it is divided by 2. It has become what? PSTB by 2. Over it is a PSTB, and here it is what? PSTB by 2. And you can see this two spectral components, it has been centered at frequency F0 or Fc, and it is minus Fc or minus F0, and this is the range, the bandwidth. So hope you understood this power spectra of your BPSK. So this waveform is very, very important, and this equation you can directly write it, which is also very important if you are going to draw the power spectra of your BPSK signal. Remember, this capital G, it could be replaced by capital S. In many books, it is given by capital S. In few books, it has been given by G. So it is one and same. It is nothing but your PSD. Now, what are the advantages of binary phase shift keying? So, advantages of binary phase shifting is it allows more efficient transmission of your radio frequency signal, better noise immunity is noticed as compared to your amplitude shift keying, and third, it is your less bandwidth is utilized by this BPSK signal comparison to BFSK signal. Moving towards the disadvantages of binary phase shift keying. Detection of BPSK signal, it is quite complex. Phase discontinuity sometimes lead to variation in the amplitude of the signal. Second, the intersymbol interference ISI present, but it could be reduced by using of filters. And last is ambiguity in the output of the signal. Now, how we can see this one? See, we have seen that this is your received BPSK signal, it is there. It has been given to square law device. Why? In order to recover your carrier signal. But suppose this is minus of this B of t, it is there. It is 0, it is there. Phase it is has been changed, it is there. But as we know, so it is a what? Negative. Square of anything, it is what? Positive. So if the received signal is negative, but the recovery of the carrier, it remains unchanged. So we don't know whether receive signal it is positive or negative, 0 or 1 it is there. So that's why sometimes it leads to what? Ambiguity at the output, that what it has been transmitted. So this problem, it can be solved by what? DPSK, that is differential phase shift keying. Although DPSK also has some its own disadvantages, that we can see DPSK later on. Now, what are the applications of binary phase shift keying? It is used in biometric operations, Bluetooth connectivity, then wireless local area network and telemetry operations. So today we have seen that why we are going to use this passband transmission model, why we are going to use it. What are the hierarchy of digital modulation techniques? We understood coherent, non-coherent, then binary, M-ary schemes. Then we came to know about what binary phase shift keying, how the generation, how the detection of your BPSK is going to take place. What is the error probability, how you are going to show the power spectra of your BPSK. Then we came to know about what is its application, what are its drawbacks, what are its advantages. So today we have seen about BPSK. This is your assignment of 5th unit. So please note down this assignment. In next lecture, we are going to study binary frequency shift keying, generation, detection, power spectra and error probability of it. For any questions, this is the email address shown on the screen. It's about our today's lecture. Thank you very much.